AI-SDM seminar. It's a real pleasure to have Akshay Krishnamurthy join us. He's a senior principal research manager at Microsoft New York. Before this, he was assistant professor at UMass for 2 years, and before that, he was at
your student.
he was at SMU. So welcome back. And one thing about him that's really great is he's really, despite being at Microsoft in a industry, he's really like continuing to be really a core foundations person. So we really think of him more as an academic person, and really look forward to hearing about his latest work.
Thanks, Arti. Thanks, everyone. It's really great to be back. I realized I haven't been back to CMU for like, I don't know, 7 years or something. So it's nice to come back. I still remember some buildings and all that stuff. Okay, so the talk is about this thing called this coverage principle, and it's, I guess I'll tell you about it. The talk is actually extremely modular, so please ask questions and we can just stop midway, or there'll be some point where I'll ask you which part you want to hear and we can decide what to do. And yeah, this is just about some work that like me and this group at MSR NYC have been working on, just to like kind of understand what's going on with language models, try to maybe help practitioners understand what's going on, and maybe we can do some algorithmic intervention, but we'll see. We'll see. That's harder, I think. How do I change the slide? Yeah. Maybe not. Okay. Okay. So to just get started, I like to always give my cartoon of what a large language model is, or like at least how they're trained. So maybe all of you already know this, but there's usually kind of like 3 phases to the language model training pipeline. There's pre-training, post-training, and inference time or test time compute. Pre-training is this phase where I'm a bit confused about. Oh, wow.
This is a Microsoft laptop.
Yeah, but it's not my laptop. I lost my mouse.
Oh, it's a
Okay, cool. Does that work? Maybe I should just keep them out. That quick slide. Okay, so let's keep going. Okay. So in pre-training, you sort of teach the model how to read. You give it sentences, and you have it read the first part of a sentence and try to predict the next word. You do next token prediction. This is this regime that's very compute and data heavy, and so the algorithm is somehow very simple. You just do next token prediction. It's maximum likelihood estimation. Post-training is this more data scarce regime, and because there's less data, there's somehow more algorithmic diversity. So there's all sorts of things that people do here. They do, preference-based fine-tuning. They do all these other things. Basically, here you're trying to get the model who the model kind of knows how to read. You're trying to get the model to follow instructions, not produce toxic content, do all these more like steering type things. And the last phase is inference time or test time compute. Here you actually have no data. You just use the model in some non-standard way. Like maybe you've seen stop prompting, or you do multiple samples or something like this. And somehow by doing this, the model has better performance. And okay, this test time compute thing was popularized, I think, maybe with this DeepSeek R1 paper in 2024, or I forget, 2025, recently. And it's sort of a new way that people are using language models. And so one theme of this talk is that maybe we have this new way of using the language models, and it's sort of not aligned with the way they were trained. And maybe we should be rethinking this. I know that he likes this. So, maybe we should be thinking about, should we be changing the first 2 stages given that we have this new 3rd stage? So we'll get to that, I guess, a little bit. But first, let me tell you a little bit more about inference time computation. There's many ways to do this. I'm going to use one, maybe the simplest one, which is called best event sampling. So what you do is you ask a language model a question. Language models are like stochastic, so they can output different answers. So you sample from this conditional distribution, you get many answers, and then you choose one, maybe by asking a verifier, or maybe asking the language model itself which one is best. And you pass this to the verifier, you get something. This is called best event sampling. This actually works quite well. So just in and of itself, it's a good thing to do. This is an experiment that we reproduced from this large language monkeys paper. So here I have a bunch of language models. I am changing n, how many samples I get per question on this math reasoning data set, and I'm measuring whether how many of these, what's the accuracy on the test. So you generate 8 samples and you ask, is any one of them correct? And for Mistral, which is actually quite bad, like 65% of them are correct. Or no, on 65% of the questions, one of the answers is correct. Okay, and so you see, okay, like if you increase inference time compute as measured through n, you can do much better than you would see just from like one sample. And maybe that's fine, but you actually can do much better than standard decoding strategies like greedy decoding. That's what I'm showing you in the line here. If you generated one sample in the most standard way, you'd actually be doing quite poorly, I guess, relative to what you could do through sampling. Okay, so that's one reason you might like best of n sampling. There's another reason, which is a little bit more tenuous, but there's some idea in the literature right now that best of n sampling is very predictive of how the language model will perform after post-training via reinforcement learning. And this is this thing called sharpening. And let me just show you sort of what happened. So this is an experiment that we ran. Sorry, it's a little bit blurry. So what I'm showing you is these best of n performances, pass at n curve for a base model, and the same model after we post-trained it using reinforcement learning. And what you sort of see is that like the base model actually, the post-trained model actually cannot improve on the right side of these plots. It somehow this pass at n performance is some like skyline for what the base model can achieve. And this is this idea of sharpening. Basically, all you can do is you can improve the pass at n for low n, but you cannot improve the pass at n for high n. That's called the sharpening phenomena. Okay, there's some debate about this, and we can talk about it later. But maybe for now, like pass at n is also somewhat predictive of how RL post-training, which is sort of now the standard way that people get these fancy reasoning models.
Pass at n, but with perfect oracle, right?
With perfect oracle, yeah. So for the whole talk, I'm going to talk about perfect oracle. Good question. We did some work on imperfect oracle. It's a good question. I'm thinking about this modularly. There's a question of how do you do test time compute with the perfect oracle. There's a question of how do you test time compute with the imperfect oracle. Maybe if you can solve one, you can have some ideas that help solve the other. But yes, perfect oracle. Any other questions? Okay. So yeah, maybe this is a bit debated, but for now we can maybe think of pass at n as being predictive of how the model will behave after RL, and doing like basically this GRPO thing is sort of how you get these fancy reasoning models like O3 or DeepSeek or whatever. So this is sort of the current thing that Frontier Labs are doing, I guess. Hard to say. Okay, so let me just drive this point home with a cool experiment I saw from this paper by Ayush Karan and Yulin Du. So this is the thing I showed you on the last slide. This is what they did. So they have a base model. They post-train it using GRPO, and then they measure, so then they collect some responses from the GRPO model, and they measure the probability of those responses as measured by the base model. So they say, what is the base model's log probability of producing this response? And what they find is that GRPO is just sampling things that the base model has high probability of doing anyway. There's no, okay, so let's look at this light blue. All of the stuff that GRPO does has very high likelihood under the base model. There's nothing coming from the tail. So that somehow GRPO is really only just finding these things that have very high probability under the base model anyway. So this is like, I think, fairly compelling evidence that this thing is doing sharpening. Okay, so this thing is doing sharpening. So maybe like this pass at n is a kind of interesting thing, but we should sort of understand it a bit more. Here I want to highlight two things that I think are kind of weird. So the first one is that these pass at n curves can actually cross. So here I'm showing you these pass at n or best of n performance for two models that MSR produced. That doesn't matter. They're actually the same size. And one is sort of phi3 medium is the older version of phi4. And okay, that, if you look to the left of this curve, you'd be like, yeah, the newer model is better. But if you look at the right of the curve, you're like, actually the older model is better. And that's kind of weird. And it might even suggest that if you were to like try to turn one of these into a reasoning model using reinforcement learning, maybe you should start with the orange guy, phi3. So that's kind of undesirable. Maybe you'd like to say that the pass at one performance is predictive of what's happening on the other side of this plot, and it's just not the case. Okay, so that's one thing. This thing is a little bit worse. This is a paper out of Surya Ganguly's group. I'm literally taking their data and plotting it in a different way. They train a language model, again, on the math task. What they see is, and I'm showing you like the training over the course of, training, the pass at one performance is monotonically improving over training. The pass at n for large n is actually monotonically degrading over training. Somehow this is very bad. Maybe you should not train the model this long. You should not train it very much at all.
So I get the reason why that might be happening, but do you have any intuition what happened between C3 to C4 series of models? Just like extended,
I think it's the same phenomenon.
same?
Yeah,
like
so it,
more training.
well, it didn't get more trained, but it's like confident and wrong. I'll show you some diagnostic
Okay.
of this later.
Yeah.
Yeah. Okay, so all of this is to say, like, maybe we should be understanding this pass it in thing more, and in particular, what governs pass it in. Any questions? So that's gonna be the purpose of the talk. We think pass it in is this interesting thing. It's sort of predictive of RL performance. It's kind of useful in its own right, but it behaves pretty strangely. And so maybe we should understand what's going on. Okay.
A great question. Why don't we train with that as a metric? Like,
Yeah, we'll come to it. It's not so easy, I guess. Yeah, yeah.
what n are we talking?
That's part of the problem. The many ends, I guess, right? Yeah. Yeah. Yes, but this for some silly reason, which is the model has support everywhere. And the model cannot assign zero probability to anything. Right? So that's not very interesting, right? You want it, yeah, so right, so like everything will converge to one. The model has some non-zero, but exponentially small probability of producing the right answer. You sort of want it to be only polynomially small. That would be nice. Okay, so this is the plan for the talk. I'm gonna introduce some new quantity that we're gonna argue actually is predictive of pass it in and like governs the post-training performance of these models. I'm gonna tell you some like theory about this quantity and tell you that when you pre-train using next token prediction, you actually get this kind of for free. And then in the end, I'm gonna switch gears to something a bit more empirical and tell you that you can like do exploration to improve RL and coverage. And we'll see how far we get. Okay, so language models are very complicated. I do not like that. I mostly think about language models using this very silly abstraction. So I'm just always thinking of a language model as some conditional distribution over responses y given a prompt x. This is hiding all of the gory details of what a transformer is and all these things. And for most of the talk, it doesn't matter, which is great. And we're going to interact with this true reward function, r star, that is known. It's a function of the response in the prompt. Okay, and in this setting, you can just define best of n. You sample n responses from the base model. You choose any one that has reward, and you return it. Okay, that gives you a policy. That's what I'm showing you here. I'm running this algorithm, and I'm telling you how it works. Okay, so the first question we're going to ask is, what can you prove about this algorithm? Or when will it work? And for this, we've defined some notion that we call the coverage profile. So this is some quantity, some like, distance or whatever between two policies. One is pi t. You should think about this like a policy that has good performance on your task, achieves good reward. And pi is your policy, your pre-trained language model. And what I'm going to ask is, okay, if I sample questions from some data sets and I sample responses from pi t, how often is it the case that my model is close in density, has good density ratio to the pi t? How often I should be within a factor of n for some parameter n to the coverage? This is your question. Which n? Good question. So that's it. I want to say I mostly have reasonable probability of sampling the things that pi t samples.
Same in
This is a parameter to the quantity, and this n will be over. These two n's are the same. They are the same, and you should think about this as basically the n in best of n. It will be off by some log factor for some union boundaries. Okay, yeah.
pi y given x is the probability.
It's the probability. I guess you can take log of everything, and it's fine. Also, you take log of everything you decide. It's when everything that you play, I play with at least 1 over n that mass. That's what it is. So my density can be at 1 over n less than yours, fraction less. I'm covering. I'm not over. I'm 1 over, yeah.
Pi t is like Oracle policy or like any policy?
So for the theorem, it's any comparator policy. I think the most illustrative is when it's the policy that gets high reward. Good. Okay. So what we prove is that it's not hard to prove. What we prove is that this quantity is somehow necessary and sufficient for best of n to succeed. Maybe this is a question about which n. So I want to bound like how much reward does pi t get versus how much reward does my best of n policy get. And this will be upper bounded by the coverage, okay, so there's an n here. There's coverage with parameter m plus epsilon, but this m is kind of like the same as n, up to some log factor. So you should, I think kind of it's okay to think of n and m as about the same. And so I want to say like in n sampling attempts, I mostly cover everything that pi t would do. You have to pay for some unit bound. Okay. And the lower bound is very similar. The difference in reward between the task-specific policy pi t and the best of n policy is lower bounded by the coverage at some slightly larger space. Okay, and if you have worked in reinforcement learning or covariance shift, some quantity like this should seem kind of familiar to you. These density ratios can sort of pop up in lots of places. And so maybe you've seen something like this. If you haven't, let me just give you some intuition through like a toy example. So that's the definition. Let's work in a special case. So pi t and the reward function are spiked on one correct response to your question. So they're both one hot. And in this case, you can simplify everything. So coverage at scale n is like 1 minus the probability that my policy plays the correct answer. Like what's the probability that my policy plays the correct answer? It should be at least 1 over n. This is just some rearrangements of that guy. Okay, and you know the best of n performance is actually exactly this passed n quantity, which is this thing. I average over samples. Okay, if I want to get the answer right in n sampling attempts, I should pay some binomial thing, right? So I asked in n sampling attempts, what's the probability that all of them are wrong? It's exactly this. And now maybe you can sort of see why these two things are related. This one is sort of like a thresholded version of this one. Like if my probability is at least 1 over n, then you would expect this thing to be about 1. So that's okay, that's like how the proof goes. Okay, let me tell you something a little bit like why do you get these crossing curves? So first of all, if you look at passed n and coverage, they're both monotonic transformations of like the correctness probability of my policy. And so if I just have one question, then like there's no way you can get crossing curves. Like if I'm better than you at time 1, then I should be better than you at all times, at all n. And if I dominate you point-wise, the same thing would be true. So obviously what's happening is that we're not like these two policies that have crossing curves, they're not dominating each other point-wise. So that's like this plot. And indeed, if you look at the correctness probabilities for these two, that's what I'm plotting over here, you see that 5-4 is very much spiked. Many of the questions it gets right like all the time, but there's actually quite a few questions it gets wrong a lot. And 5-3 medium actually does not do this. This number is much lower, and passed n for high n is sort of like picking up this part of the histogram, and passed n for low n is picking up that part of the histogram. And that's why you get crossing curves.
Not oracle. Isn't that part of oracle? Just because 5-4 is more accurate than sort of like self-consistency style, oracle would work much better for 5.
Yes, I think that's probably true. Yes. This answers your question about what's going on. So this histogram, I think, is kind of clarifying somehow.
Yes. So maybe like what this histogram tells us is that like when we do benchmarking during pre-training, maybe we should, rather than looking at just one numerical metric, we should
look at many metrics. That's exactly right. So you can think of coverage is some CDF of cross entropy.
Yeah.
I'm measuring what fraction of the time is my KL big, something like this. And you want to look at the whole CDF. Yeah. That's exactly right. Okay, that's what I have on the next slide. Good job. So there's a similar story for KL. KL is like some expectation over X of something, or cross entropy is some expectation over X of something. You need to look at many different such expectations. You need to like coverage is like some expectation over X of some indicator, but you need to look at many different indicators. You're getting like a whole CDF instead of just the first moment when you look at coverage. And you sort of need to look at this because you don't know which n you want at test time. You kind of want all of them. So you should look at all of these diagnostics. And that's exactly correct. So it's some richer signal, more granular information about what your policy can do than just looking at their perplexity or the KL or whatever. It's like this. Good. Any questions? This is the part 1. So coverage is something that captures the performance of best of n sampling. It's some more granular information like the CDF rather than the first moment. Both in terms of both as compared to the passed n or passed 1 probabilities and the cross entropy. Okay, but now we train models by minimizing cross entropy by doing next token prediction. So you should ask, if this is a more granular thing, why is it actually becoming small? Why am I actually getting coverage when I train? That's part 2. Any questions? Good. Okay, so here I have to tell you a little bit more. So again, we're operating this abstraction. A language model is just a conditional distribution. We're going to think about like maybe pre-training or maybe supervised fine-tuning stage of a language model. So you have a data set of prompts X and responses Y, where X's are from some prompt distribution mu and responses are from some data policy pi d. You solve the maximum likelihood problem. This is exactly the objective of next token prediction, where you try to find some policy that has good log probability of producing the responses in your data. Okay, for now, like I'm going to focus, this is some like kind of aside, I'm going to sort of ignore some distribution shift problem. So I'm going to focus on covering pi d, and I'm going to assume implicitly that pi d covers the task-specific policy we actually care about. This is fine because actually this coverage quantity is transitive. So if I cover pi d and pi d covers pi t, then I also cover pi t. So this gives me something very grounded to focus on in some clean setting where I don't have to assume, or I'm making this assumption, but I don't have to say like, here's what pi t looks like, and so on and so forth. I say I want to cover pi d, very clean objective. So that's that. So I'm gonna solve this problem, and I want to know when does pi hat cover pi d in this coverage sense, so that when I do best of n with pi hat, I get something interesting. Okay, so the first thing you can prove, which is basically Markov's inequality, the coverage at scale n between pi d and this policy you get, I guess pi hat, or actually for any policy this is true, is upper bounded by their KL divergence on this data set, divided by like log n. This is just Markov, I guess. And maybe this is a good sign because when we are solving the maximum likelihood problem, under some assumptions, you can expect that I converge to something that is close in KL to the thing that's generating the data, which is exactly pi d. So you can maybe expect that this guy is small, which means that I get coverage, which is great. Everybody's happy. Okay, so maybe is this the whole story? I guess we wouldn't have more time, so the answer is no. So it turns out this upper bound is actually kind of ridiculously loose, and let me just illustrate this with two experiments. The first one, okay, so here's the quantity. The first one is that they're both in synthetic settings where we train transformers to do something. That something is some graph reasoning task. So there's some graph, you have to compute some shortest path. The expert produces the shortest path. You're just trying to train to follow the edges the expert follows. What I'm going to do is I'm going to change the path lengths. So I'm going to increase the horizon of the problem, or the sequence length of the thing you have to produce. Okay, so, and I'm going to show you the KL and the coverage at scale 16 over the course of training. So when the horizon is 8, you have, the path lengths are 8. Your KL goes down very nicely. Your coverage also kind of goes down nicely. They sort of track each other. When KL goes down, coverage goes down. It's very good. Very good. So maybe if you looked at this plot, you'd say, well, yeah, coverage and KL are nicely tracking each other. Okay, so now I'm going to increase the horizon. And when you increase the horizon, the KL also goes down, but it actually kind of like asymptotes at a different value. So KL is increasing with the sequence line. The asymptotic KL is like increasing with the sequence line. Coverage that actually doesn't happen. So for coverage, they all sort of asymptote at the same value. And if you think about what this experiment means in the context of that inequality, it means there's some missing H factor. The horizon should appear, you would expect like 1 over H here or something. And in some sense, that means this inequality is very loose. This is bad. Let me show you something that's a little bit worse, I think. So here's a different graph reasoning task, kind of similar story. What I'm going to show you here is overtraining. I'm going to plot the KL and the coverage at different scales. So here's KL and here's the coverage at n equals 2. And you see both of them go down. Everything looks nice. What I'm going to show you now is how this predicts the pass at n performance of these checkpoints. So I'm taking various checkpoints. Each dot here is one checkpoint. I measure their coverage and their KL on the same x-axis, and I measure their pass at 4 performance on the task. No distribution shift on the task on the y-axis. And you see that if I decrease KL or if I decrease coverage, I improve my pass at 4 performance. Very good. Both are predictive of pass at 4. Let's look at a different coverage at a different scale. So here's something very weird that happens. Coverage at scale 4, it goes down, and then actually goes up as you continue training. So you're like overtraining, but you can't tell by looking at KL because it continues to decrease. And this overtraining actually corresponds to a degradation in pass at 8 performance. So as you decrease KL, the okay, the pass at 8 goes up and then goes down. I'm plotting this, the scatter plot is a bit weird, but like the points at the top left are actually these. They're the points with the low coverage at scale 4. So this quantity is somehow much more predictive of pass at 4 performance than KL, and KL can actually be like anti-correlated or something.
What's 2 and 4? These are horizon.
No, coverage has some parameter.
Oh,
So that's the parameter for coverage. We're using some like guess that coverage at scale 2 is predictive of coverage at scale n is predictive of pass at 2n. Okay, so I don't really think our theory will explain what's going on here, but this experiment I think suggests we need to rethink something. Like, you really want to stop training here, but you have no signal to do so. You can only measure, I don't know, like cross entropy or something, and cross entropy is like it just keeps getting better and better. So how do you know to stop at this point? Because if you're going to use the model for pass at 8 or at best of 8, you're actually making it worse.
I have a question. If so, this KL is with like some approximation of the distribution. Like, let's say, like if this KL was with the true distribution, would that still be like showing the?
Yeah. So this experiment has no distribution shift, and everything is synthetically controlled. So we measure everything exact. Yeah. It's
Yeah.
okay. Maybe I'll tell you the experiment later. It's a bit contrived. Yeah. It's clean, so we can actually
Yeah,
measure
yeah.
things very carefully. Yeah. And maybe this phenomenon is exactly what's going on in that Surya Ganguly experiment I saw before. You're training, this number is some hidden quantity that they didn't track is going up, right? And it's resulting in a worse performance. Yeah.
Does this relate to blocking by any chance, where, the model doesn't look like it's learning, model looks on. They were also mentioning about tracking other quantities.
I think. Okay, the experiment involves parity, so grokking is definitely relevant to parity. I don't think it's what's happening here. This one is like, there's some part of the task that's unlearnable, and the model, it cannot learn that thing, so it like overfits to some other part. And by doing so, it degrades coverage on this part that's hard to learn. I don't think this can be, it's kind of morally something, there's some hard learning problem. Maybe overtrain, like training for much, much longer, you'll go back down.
But the common takeaway is we should track other metrics.
We should track other metrics. I think that's correct. Yeah.
this is over multiple fox.
This is in some online training setting. So every batch we sample a new set of problems.
So it's equal to the validation.
It's sort of like equals to validation. Yeah. Cool. Good. Okay, so maybe we can actually do everything. Okay, so those are the sort of like things that should make you ask questions about whether this bound is good enough. The answer is you can do better. So that's the first part of this thing. And once you see this coverage quantity, you can also think about, can I design algorithms that are more directly optimizing coverage? So you can maybe pick from the valley, and that's part 2B. And okay, I've never spoken about this part, so let's see how we can do it. Okay, so why should we, okay, beyond the experiments, what is like a good theoretical problem to think about why we can do better? Maybe the simplest one is just estimating a Bernoulli. Okay, so here's coverage, whatever. We're gonna estimate a Bernoulli. Clean problem. So you're gonna get n samples from Bernoulli at, with parameter p. Maybe the first thing to notice is that the expected KL for the maximum likelihood will be infinite. So there's some chance, even if p is non-zero, there's some chance that you see all zeros in your data, and then your MLE will be 0, and then the KL will be infinite because the truth actually puts non-zero mass on 1. And if p is like 1 over n, this will actually happen with constant probability. So you cannot prove a high probability bound on KL that holds for MLE, that holds for all choices of p. That's the first problem. You actually can do that for coverage. So coverage is actually always well behaved, even though KL can have this sort of like pathology in the tail. And maybe here's why. So if n is sufficiently large, then KL will also be well behaved. So if n is sufficiently large, you can, I don't know, use Bernstein's inequality to show that the MLE, the fraction of ones will be like at least p over 2. And so the coverage will be controlled. And if n is actually really small, then the probability that the data produces a 1 is tiny. So you can write off this missing mass in the coverage quantity. All right, so the coverage at scale n is just less than p because the data never produces a 1. So you have this missing mass phenomena you can write off. So the idea is that missing mass somehow blows up the KL when coverage is always between 0 and 1. There's no range dependence in some sense. Okay, so that's sort of why you should hope to be able to do better. Maybe just to point to this horizon thing, in sequence models, you're making predictions over many tokens. The range of the random variable scales with the horizon. This is exactly what's happening. Yeah.
Is it because of your definition of coverage? Like, because KL has a lot in the quality ratio, if you use, I don't know, chi-square or something.
You just want something that's bound. I have an indicator, actually. The real thing is I have an indicator in this coverage. I have expectation of indicator that the ratio is big. Right, so log, even the chi-square will have density ratio that can also blow up, right? But yeah, like, it's just we wrote something different. I mean, yeah. Yeah. Okay, so the main statistical results in the paper are just like generalizations of this phenomena. Let me tell you one of these theorems in some special case, just because it's kind of clean. So the setting will be autoregressive linear models. If you're in Dhruv's talk, he talked about them yesterday. So we're going to generate H tokens sequentially. The way we're going to do this, there's going to be some fixed feature map that's phi that takes the prompt and the tokens you've generated so far and the current token you're considering generating, maps them to d dimensions, and you sample from this distribution that's like a softmax of a linear function of these features. I guess this is the cleanest model for autoregressive generation. It's parametric, I guess, and so on and so forth. Okay, so that's the model. The first thing you can show is that in this setting, you can prove a lower bound on the KL for maximum likelihood. You can show that there's some problem where the features are one-dimensional, but the KL scales with horizon over n. So at least you're in a setting where you should be able to, hopefully you can see some separation. And this is maybe what's happening in this picture. And in this model, we'll prove two things. So let's assume we're well specified. That means that pi d, the data generating distribution, is an autoregressive linear model. The features are bounded in norm, and I'm going to not define this quantity, but there's some notion of variance that one of our bounds will scale with. So the first thing you can show is that if you're in this low dimensional regime where you're willing to pay explicitly for the dimension of the feature map, you can show the coverage is bounded like this. Maybe the point is there's very, very mild H dependence. It only appears in log factors. And you sort of get d over n with some log factors that are very benign. And in high dimension, you can prove something else. So high dimension means you don't want to scale explicitly with the dimension of the feature map. Instead, you'll pay for the norm of the features. You can get this bound. And here you're paying for something that I probably won't tell you about, this sequence variance. But you also get like pretty significant improvements as you increase the capital N parameter in the coverage definition. So coverage is getting, it's converging faster as you look at higher and higher thresholds, which is the other phenomenon sort of that was interesting. Okay, so basically in both of these, there's sort of no explicit horizon dependence. This sigma squared in the worst case can scale with the horizon, but in many problems seems to be much less. You get some improvements if you increase the capital N parameter. Okay, like maybe for the high dimensional case, maybe for the low dimensional case, you can go all the way to like roughly like 2 over n, which is cool. And you can get some very large improvement. You can actually sort of kill off the slow rate term entirely if you're taking n to be big n, which is kind of cool. So you can get like fast rate for n to be large. Okay. Let me tell you how we prove this. Okay, let's see how it goes. Okay, so the idea for the proof is something like this Mendelssohn small ball method, where you do some like one-sided concentration. If you don't know what any of this means, you can just close your eyes for 2 minutes. Okay, so the idea is we're going to say if coverage for some policy is large, then some empirical version of coverage is large. And that means you have to have low likelihood, which means you can't be the MLE. That's the high level idea of the proof. Most of the concentration is going to happen here. And the point is that coverage and the empirical variant will be bounded in 0, 1, so you won't pay for the range. And there'll be some very mild concentration over here that you also won't pay for the range. Okay, so here's some empirical version of coverage. It's like, I guess the first thing you'd write down. How many times does your policy pi not cover pi d on the data you've seen? You can do like Bernstein's inequality plus a union bound to show that this concentrates to this with some coarse concentration. You don't pay for the range here. And then, okay, so now we're going to look at maximum likelihood. So you're going to look at this log ratio between the policy pi and data policy pi d. We can look at, let's look at the times when like this sample is in Sn. So if the sample is in this set, this uncovered set, you actually get a negative log n contribution, which is great. And otherwise, you can do some kind of standard MLE analysis, but you only look at one side of this MLE thing, and it's the easier side where you don't have to pay very much. This I won't tell you about. So what you can show is that the empirical excess risk is bounded by like the number of times you're uncovered, times minus log n plus some other concentration term. And you plug this in for this, and you rearrange, and you'll get the coverage is very small. This is kind of the bound. Okay, you can open your eyes again. Okay, so that's all I wanted to tell you about statistical theory. There's a lot more in the paper. My colleagues went a bit crazy, and they proved lots of fun things. But this is sort of like the conceptual points. Let me tell you a little bit about algorithms, or maybe any questions. Good. So now we have this coverage quantity, and KL does something, but maybe you can ask, can we do better? Like, minimizing doing next token prediction does something, but maybe can we do better? So here's one idea that we worked out. It's something like test time training. So here I'm writing this more explicitly as a next token prediction objective. So if you expand, you do chain rule on, this conditional probability model, you'll get some objective like this. I'm gonna optimize this with stochastic gradient descent over a single pass at the token level. So I'm going to take like one token, I'm going to take the gradient of the objective with respect to one token, and I'm going to optimize and get theta hat. And now at test time, I'm going to do this thing called test time training. This is this thing where you train on the tokens you generate during inference. So I start with the solution that I got from SGD. I generate one token by sampling from the distribution. I treat that token as true, and I take a gradient with respect to the log loss or log probability of that token, and I update my weights to get theta hat 1. And then I generate another token with theta hat 1, and I do it again. So over the course of the thing, I generate theta hat 0 all the way to theta hat capital H. Each token is generated after doing one gradient step. I'm changing my weights as I'm generating. And then to generate a new sentence, I reset my weights to the beginning.
But then in this case, like this, the YIs which already have a high non-zero coverage in the base model, they will only get upweighted, right?
That's right.
It's
So
like entropy minimization.
It's kind of like that. That's right. But now I'm generating a different token, right? I'm going to condition on this in the next stage.
But how will this improve the coverage?
A good question. It's hard for me to say. It does a little bit. I don't actually have good intuition for this one, but this is what you can prove. Turns out it's actually better than what you can get from MLE. Basically, this log n is sitting outside of the square root, and it's hitting the 1 over n term. I don't have good intuition for why this happens. Yeah.
Isn't this also doing sharp?
It's kind of sharpening.
Yeah.
Provide better.
I don't know. We can try to work it out later or try to gain some intuition later. This is what I guess you can prove. Let me show you the other one because it is attached to the experiments a little bit. You can see better. So this is checkpoint selection. So I showed you this experiment before, and you kind of want to like find the, you want to pick one of these checkpoints in the bottom of this valley if you care about pass at 8. How do you do it? The thing is, like, coverage is not something you can actually measure because you need the probabilities of you need pi d's probabilities, and you don't really have these. Same as you can't really measure KL, but you can measure cross entropy. So what can you measure? We don't know, but you can do something like, so you do this training run, you take all the checkpoints, and then you run some procedure to try to select the checkpoints. And the procedure will be some tournament. So you're going to measure some empirical version of coverage. And you're going to say, can you find me a policy pi who kind of covers everybody else? That's the idea, where it covers everybody else is sort of with respect to the data. If you've seen these like Sheffield estimators, it's kind of like that.
But your pi prime is other checkpoint.
Other checkpoints, yeah. Okay, and there's who's generating the responses in this code hat? It's the data guy, the data policy. So there's some third argument. Okay, so that's the algorithm. This algorithm you can prove something about. So it actually ensures coverage competitive with the best policy in the class. So it actually gives you some sort of like agnostic learning guarantee. Even if you can't realize pi d, you can actually get something non-trivial. And so maybe that's more reflective of what's happening in the experiment. And you can run this thing. It's like something you can actually run. And it kind of works. So we ran it. I'm showing you many training runs. And each one I run one of these tournaments. And I end up picking out all of these guys. And that actually kind of picks everyone in the bottom of the valley.
So this is solving a minimax game, someone.
Yeah, but you kind of enumerate. So I take, 100 checkpoints and I just solve this 100
All
by.
pairwise.
Yeah.
Oh, wow.
But I only do like 100. So yeah, it's not like, you're not gonna train a language model this way, right? You're gonna train a language model using SGD on log loss, and then you're gonna pick when to stop doing something like this. So there's a good question that like, how do you turn this into like a training algorithm? Or how do you train for coverage? I don't know how to do that.
You're not picking when, you're not doing this online, right? This is post-hoc.
It's
You're
post-hoc,
picking when to
yeah.
stop.
Yeah, you're saying I'm gonna train for a very long
Yeah.
time. So I'm not saving compute.
Yeah.
I'm running for a very long time, and then I say like, which iterate should I have stopped at?
But it's like quadratic number checkpoint.
Quadratic and number check.
But you're assuming one of the five primes is close to 5t or 5d or.
Yeah, it's kind of like a regret bound. You compete with the best thing in your set. Right, yeah. So yeah, if your set is bad, then probably you shouldn't expect to get anything, I guess, right?
Can we get an idea how bad it is from our part of it is, because we don't know how.
No, because you can't measure coverage. Yeah, so that's a problem. So what to measure, I actually don't know. Like if you have a synthetic problem or you're doing distillation, maybe you can measure coverage because you can get the log probs of the teacher. But if you are just pre-training, you can't get the log probs of the data, that you can't measure this quantity. Okay, there's maybe in the back first.
So why is it a benchmark and not a match? Then I think I got a paper loss there.
Okay, so coverage is a thing you want to be small. Okay. No, it's very confusing. I actually had it written wrong the other time. So this is coverage. I want most of the time this event is not true. So I want coverage to actually be small. I want to find the one who it's very confusing. I actually wrote it wrong on the slide first. So yeah, so coverage is a quantity you want to fit. Okay, good. So I think this is sort of what we've done. There's some new statistical theory that you can prove for this coverage quantity. It's kind of interesting. There's new algorithms. Okay, they're kind of, you can critique them. I think there's just a lot more work to be done. So I think it's kind of interesting. Can we make these things more practical? Can we do like gradient friendly training? Sorry, I missed your question.
Yeah. Can we do some relaxation by very
Maybe, I don't know. Yeah, I think it's open. We stopped because we wanted to.
It's something how to deploy a convexel.
I mean, you just want small.
You can just, yeah.
I mean, it won't give you, it won't give you.
No, I think we should think about these things. I don't know the
Yeah,
answers. I think we should think about all these things and see if there's something interesting to do. Yeah, go ahead.
No, I think maybe people would say super and take average of the model wins.
Yeah.
Sometimes.
Kind of works, right?
Yeah.
It's weird way. Okay. Okay, so I'm gonna shift gears. This is a bit more empirical, and I'm gonna tell you about some other thing we did about improving coverage through like exploration. Okay, so for most of the talk and most of my life, I think of a language model as a conditional distribution. I gave some talk at some point and someone was like, why are you thinking about it just like that? There's much more structure. That is obviously true. So a language model is actually like something much richer. You can do all sorts of crazy things. There's a attention and there's hidden representations and you can access the probabilities, you can access the logits, you can steer, you can do all these things. Maybe we can use some of these things to actually get the model to just produce more interesting things and maybe cover responses better or something. So can we leverage the signals to improve the coverage of the policy without training it? So I'm going to tell you something that's like kind of like that, but a little bit sketchy, I guess. So here's a problem that's like motivated by trying to solve this problem, but it's a little bit easier to iterate and try things out. It's called inference time selection. It's kind of subsampling. So I'm going to take a policy, going to generate a huge number of responses, take n to be very, very large, 10,000 or whatever. You generate n responses. You want to look at them and some signals coming from your language model to subselect far fewer of them, k, and then measure the passive k performance of what you saw. Maybe if you can solve this problem well, you can directly generate the k. Maybe if you solve them well, you can actually like use how you did it to just do reinforcement learning or whatever. So we're using this as like some test bed to try things out. And then we'll see if we can do it once we have a good idea here. This is very easy because you generate one pool one time and then you run all these algorithms just off the shelf. You don't need to actually spend time on a GPU or whatever. Okay, so okay, it's not rendering well. So anyway, this is some, I guess I'll tell you what we did, but so you generate a bunch of prompts. What we do is we're gonna actually take their embeddings as like from the language model. These are gonna be like, you know, you pass every token in, you get some vector right before the unembedding layer. You average all the vectors along the sequence, you get one vector at the end. So every response has one vector. And then, okay, average over token. And then we're gonna run some optimal experiment design strategy, which I will, maybe don't look at the picture. It's this thing. So you're going to start with like a matrix that's the identity. You're going to find a response whose embedding has large inner product under the inverse of this matrix, and you're going to update the matrix. You're like sort of building this ellipse, and you're finding things that hit the directions where the ellipse is small. Okay. If you've seen experiment design, maybe you've seen this before. Okay, good. So that's what we're going to do. That's it. Very simple, kind of theoretically principled. It works pretty well. So what I'm showing you here is on every, okay, I have like one model. This is V4, that's some Quen model. This is some coding task, that's a math task. I'm showing you, if you just did random sampling from the base model, how many samples would you need to hit the correct, to get one of the answers to be correct? And if you did this course set strategy, this optimal design strategy, how many samples would you need to get the answer correct? I'm doing this on a per question basis. So each dot is one question, and we did some multiple seeds and stuff to average everything away. And I'm scattering all of these, and I'm plotting some line of best fits. And what you see is actually like most of the points are below y equals x, which means the exploratory thing is better. And this is a log-log plot, so like, you know, the things that are lower, it's actually quite significant that you're saving like factors of 5 and stuff.
I have a question. So like this is a great result, but like so I'm assuming verification cost is negligible, right? Since like I have already generated. So what is the like end goal here? Because I think you mentioned you want to use these results to then like maybe change the sampling strategy itself going forward, or like RL something.
Good. So I'll show you some RL results. So you can use some optimal design idea in the RL training loop.
Okay.
I'll show you something. It kind of works. We actually ran one experiment where you use this optimal design idea to directly generate. So you, at every token, you measure some ellipse, then you find the thing with the largest inner product or whatever. That also kind of works, but our implementation is quite bad. So actually writing some CUDA kernel to get this to be fast and competitive with anything else, that's something we want to do. We haven't done it yet. So this was just like, we can iterate quickly. And then we want to do this harder engineering stuff and longer training runs.
So that ellipse is basically like sampling the core set, right? Basically.
Yeah. So there are some settings where actually doing verification is very hard.
Yeah.
So maybe this is directly useful there. But we're also thinking about this as like a stepping stone to some other stuff. Okay, this is just some aggregation across many tasks and many data sets. I'm aggregating across all the questions in each data set. You see most of the points are below the line. Actually, the weaker models are the ones where this doesn't work, and it's maybe because their embeddings are kind of poor. So if you have a good model with good embeddings, you actually get maybe like factor of 5. I think that's like factor of 5 improvements, something like that.
Sorry, I zoned out. The exploration is done by some sort of LinUCB.
It's like LinUCB. It's like LinUCB, yeah.
Okay.
Yeah. It's like you're not actually interacting. So you select them iteratively, but you never actually measure their reward. You just find the maximum.
You just have to
find the maximum volumes. Yeah. Cool. Okay, so you can also ask maybe these other things that people do for sampling actually help. Okay, maybe some reviewer asked or something. And so we tried this. So what I'm doing here is each plot is I generate samples from the base model using some standard sampling scheme that is in every language model library. Like vanilla is like temperature 1 sampling, so on and so forth. And then the dashed line is the pass set end performance of exactly that. The solid lines are the pass set end performance of then selecting a core set on top of that data pool. So like, okay, here I'm doing min p sampling, which is something I hardly know. And then I'm running this core set selection thing on top of the Minty sampler. And what you see is actually like, okay, this curve is actually better than all the shaded curves. So just running core sets on top of vanilla is actually quite good already. And okay, except for high temperature, every shaded curve is lower than every solid curve, basically. And so this kind of works regardless of how you generate the original pool using standard ways to do so. And even just using the original pool is kind of good. Again, to your question, like you still want to do direct generation. We're not doing that here. Okay, so maybe this idea is kind of interesting. Maybe you should ask, can we do something for real with it? And so we tried this, we put it into like the reinforcement learning training loop. So we're going to use experiment design as an exploration bonus in RL. Here's a cartoon for what RL does. You sample a bunch of things and you train on the ones that have high reward. That's it. So here I'm going to sample a batch and I'm going to create like an internal reward or intrinsic reward based on their, some experiment design criteria. So I'm going to set the reward to be the true reward plus something like the contribution to the ellipse. And I'm going to train on this. Sample, compute this thing, train on the ones that have high reward. That's the algorithm. It kind of works. Again, the picture's a bit grainy. But okay, so gray is the base model. Blue is basically this where beta is 0. So this is like the standard RL recipe. Green is this where beta is, I think, 0.5. And what you see is actually you sort of are like the pointwise max of the two of these, which is kind of cool. So you actually don't degrade the high-end performance, but you mostly recover the low-end performance of RL training. Good. Okay, and maybe since sometimes people ask me, I'm not really advocating for this method in particular. I'm mostly saying we should explore doing exploration in this framework or in this like RL post-training thing because it seems to do something kind of interesting. I would actually find it really cool if you can sort of get above somehow. For some moderate end, you can actually get much higher. That's a sense that you actually are like learning new things. Here, I just like, I'm not losing what the base model already learned, but I want to actually learn new things. And yeah.
I have a small clarification question. So like, am I correct to assume that like, if I would have like, probably this is a compute match, but if I would have run like the beta equals to 0 setting long enough, I would match the beta equals to 0.5, like sampling the important.
I don't know if that's true, actually.
I see.
I think there's some
Because like
optimization
you're just,
issues.
yeah.
Yeah, I
Barring-
don't think that's true.
I see.
I hear talks about where the temperature is super important, it shouldn't be too low, right? That
For the sampler.
sweet spot.
Yeah.
Isn't that exploration the same thing that we talk about? Like, is this under temperature 0 and you're adding some exploration, but if temperature was.
No, it's like temperature 0.6, which I think is like the standard one. Maybe this experiment maybe provides some signal that this thing is doing something different, slightly different than changing the temperature. It's something a little, like you're actually doing something, I don't know, like finding more interesting responses than temperature sampling. But yeah, I think that is some version of exploration. This is some other version. I would actually love to see more experiments about even just temperature. How does that affect? Okay, I'm basically done. So, I didn't say this word before, but somehow this is something like hidden knowledge. So a language model is not just a conditional distribution. You shouldn't, okay, it's nice because it's clean, but there's more information, there's more structure. There's ways to extract knowledge from the model without, training. There's no new information. So you do some computation and you get something better, hidden knowledge. One way to do that is to use the embeddings. Embeddings provide some signal beyond what the samples produce. Okay. So that's it. So that's just to summarize. I think test time scaling calls for us to rethink the pipeline. I think this experiment is pretty interesting. I told you about this coverage concept. It governs best event performance. It's implicit. You get it from the next token prediction. Maybe you can improve it through training or through like test time exploration. Some questions that I'm curious about. I've mostly been using best event as a surrogate for post-reinforcement learning performance. There's some evidence that happens. There's some evidence that it doesn't happen. It's a bit murky. So what's really going on? I don't really know. you know, RL is not one thing. There's many different recipes. There's ways to curate data. There's different algorithms. So if we can actually bring some clarity there, I think it'd be quite nice. And then most of this I've actually been thinking about test time scaling as repeated samples, but actually very few people do this. Most people just generate one very long trajectory. And so that's like you use a super long chain of thought. And I mean, people do things that I find a little bizarre where they actually like, the model wants to end its sentence and you say, no, keep writing. You actually intervene, you remove the end of sentence token and you say, wait, and then the model writes a bunch more, which is like, the model didn't even want to do it, but it works. I don't know. So what's going on there? Why is it that when I train a model to produce sentences of length 128 and I actually use it to produce sentences of length 1024, it's actually better, right? What can we say about this framework? Can we write down some abstraction, some mathematics for this and say something interesting? That'll be fun. And let me just finish. Okay, so here's some references of the papers. If you're going to NeurIPS, Dylan, Adam, and Max, who's here but not here, are giving a tutorial on imitation learning and discussing some of these things at NeurIPS, and a bunch of us are running a workshop on reasoning. Let me acknowledge the collaborators. So like interns, Fan, Audrey, Jens, postdocs, Sadika, Noah, Adam, and longtime collaborators and researchers, Dylan and Jordan. Thank you.